So we are looking at word problems and kind of identifying that something you need to do would be to use the series formulas. All of these could also be done with sigma notation, because we know that's another way to find the sum, but because the topic of this lesson is series formulas, that's the way I'm going to do them. So the first one says a person places 1 cent in a piggy bank, 1 penny in a piggy bank on the first day of the month, 2 pennies on the second day, 4 pennies on the third, and so on. Will this person be a millionaire at the end of a 31-day month? So first, we know on any of these sequence or series problems that we want to try to represent our numbers as a list. So that's the information I have. In order to know if the person is a millionaire, we need to know the sum of all the different money they have. So we're using an S sub n formula, not an A sub n formula, which is the first kind of decision you have to make. The next decision is, do you think this pattern is arithmetic or geometric? And I can see that I'm multiplying by 2 as I go down this list. So it is geometric. So this is my geometric series formula from my reference sheet. Remember, we changed the r's to a b, so we can really know that that's the base of the exponential function and not just a percent. So working from here, I am adding up a 31-day month, so I'm finding S sub 31. So that is start value minus start value times the multiplier, which is 2 to the 31st over 1 minus 2. Remember, those 0.01s don't cancel because the second 0.01 is multiplied by the 2 to the 31. So when we go to find the answer to this, we basically just type that in our calculator. This is kind of a classic problem. This comes from a classic problem that says, do I want to get $100 a day, or a penny the first day, 2 pennies the second day, 4 pennies the third day, and so on. And the better choice is always that doubling or exponential pattern, because in this case we get $21,474,336.47. So a lot of money, so yes to the millionaire question. The next one says Miss Natalie earns $200,000 per year and her salary increases $400 per year. How much did she earn at the end of the first 15 years? So I don't like the wording of this question. We usually see on these something like in total, or maybe even how much has she earned. So something that says, I don't really want to know how much she made the 15th year. I want to know the sum of all those. So be looking for this word total or sum or something that tells you want to keep all the money. So the wording of this one's a little ambiguous. I do think it leads towards a sum, but not as clearly as it should. So we have a sub n because we're adding up the amount from the first 15 years. Since we're increasing by a linear amount or an adding amount, we are going to use the arithmetic summation formula. So that is n times a sub 1 plus a sub n over 2. So this one is actually a little trickier to find. We're finding a sub 15, and you'll see, first off, my n value is a 15. My start number is 200,000, but I don't know a sub n. And the biggest thing I need to make sure I understand is that a sub n, in this case, means a sub 15 because our n value is 15. So I'm going to need to use an explicit formula to find that. So my explicit formula states that I start with a common difference, which is 4,000, times n minus 1. So n minus 1 is 15 minus 1, or 14, plus a sub 1. So that is the arithmetic explicit formula. And that's going to give me that I have 256,000, or that's how much she makes in the 15th year. When I take this in, I am going to get that the amount of money she's made over those 15 years is equal to $3,420,000. And if that seems like a lot, if we just did 200,000 times 15, we would get 3 million, and then the extra is from that increase in salary each year. So example 9 or exercise 9, is one that's kind of hidden. I don't know if you saw it in a random test of a lot of different topics, if you would recognize it as a series formula, but we'll talk about why it is. So it says, in the picture shown to the right, the outermost square has an area of 16 square inches. All other squares are constructed by connecting the midpoints of the sides of the square it is inscribed within. So these are the midpoints of the blue square to make the next red square. And this one takes a little visualization, but the easiest way to see the relationship between the two squares is to think about folding in these corners of the blue square. And if I folded in those corners, I would see that these corners are equal to the area of the red square. And that basically means the area of the blue square is cut in half. So the area of the red square is going to be 8. And the same is true if I worked from this next square, which is called green square, and I folded in the corners of the red square, we would say the green square is half of the area of the red square. So this pattern will continue. The next thing I need to know is how many squares I have in here. So I've already counted 3, and then I have 4, and 5, and 6. So we want to know the total area of the squares, the sum of the areas of all the squares. So we want to add up these 6 numbers. Now this is not a hard thing to do by hand, but a lot of these questions will say express it with a series formula. So adding up 6 squares is S sub 6. I do have a multiplying pattern, so I'm using the geometric series formula. So that one says a sub 1 minus a sub 1 times b to the n, and n is 6 over 1 minus b. So when I type that in, I would get 31.5, and this is square inches. Now, when these are so small, it might be worth checking. So my next few terms are 2 and 1 and 0.5. And if I add those numbers up, I get 24, 28, 30, 31, and 31.5. So I can see that I have the right answer. The next question I threw on there because I think it's kind of a weird combination of different topics. But it is one that luckily is multiple choice, so you can do it with process of elimination. So first off, it says Jasmine decides to put $100 in a savings account each month. So she's putting 100, okay, and then she puts in 100 again, and 100, and she keeps putting this in. But each month, she gets 3% annual interest compounded monthly. So that means after the first month, this one is going to grow a little bit. And then after the second month, both of these are going to grow a little bit. Now this is tricky to think about, but the idea is actually this first 100 will end up being the biggest number in the sequence at the end. So when we start to look at this, the first thing we need to think about, because as I said, it's really hard to relate these two, but I don't just want to hide the hard problems from you that I think are a little ridiculous. We want to add up how much money she has. So we're looking for something that looks like a series formula. These two formulas would calculate how much one payment would be, right, maybe at the end of a certain amount of time, or like an A7 formula. So I'm going to cross out those two. So what I want to see here, first off, is that this one kind of looks good. So I'm going to think about this one, because I see the 1.03. So this one looks like it's an S sub 12. This is the yearly growth, but I don't need 12 years. So this one also looks wrong, because I just want 1 year. So the way I could get a 12 out, because this one also has a 12, is if I think about this and make my end months. So if I made my end months, how much is this growing per month? So when I compound monthly, that leads me to this formula. And this is going to be my base. This number is just reminding me that if I'm compounding, I get the interest more often. So if I do 1 plus 0.03, which is the interest rate, over 12, because we're compounding monthly, I do get this number. Okay. So that formula is the one that makes the most sense for the one that would work for this problem.